In this example, we have a beam subjected to a non-uniform load from the A out for about a distance of 6 feet. And at 6 feet, it has a downward force of 300 pounds per foot. And then there's no force from 6 feet over 12 feet. The connection at A is a pin connection, and at B, it's a roller connection. So what I want you to do is go ahead and pause the video and then attempt to, first off, draw a free body diagram and then solve for the reactionary forces for global equilibrium. All right, so what we need to do, so I got this free body diagram, but I haven't come up with a force that is representative of this non-uniform load. The first thing we have to realize is the magnitude of that force is equal to the area of that triangle there. So the magnitude of the force is 1/2 6 times the 300 pounds per foot, okay, which results in a magnitude of 900. All right. Now this 900, now we've got to figure out where does it act along that 0 to 6 foot. And as you recall, when we did the centroids, it's going to act in the center of that. And in this case, we know that it is going to be 2/3 over from A. So it's going to be 4 feet over from A. Okay, that's 2/3 the distance of 6 feet. And so we can replace that force for our purposes of finding the global resultant forces, equilibrium forces, for that. So now that we have that, we can use the summation of moments at A to calculate our By. And we also know that X is equal to 0 because we got no forces there. We then use the summation of the forces in Y to calculate AY, and we get 600 pounds. Okay, so now that we have that, we got enough information now to draw our shear diagram. Okay, that's the first one we want to draw. And what we want to do is we're going to draw some lines down at the ends, so solid lines, and then we're going to draw some dashed lines to represent points of interest. In this case, it is going to be at the end of this non-uniform load. All right, so what I like to do is I just grab my calculator and I just start adding numbers up as I progress from left to right. So if we look at the beam, the first force that the beam encounters is that 600 pounds. So what we do is I'll put a dot there, because I'll put in my calculator, put in 600. That's a positive number up, and I'll put that dot there. And then as I progress left to right, it is subjected to that non-uniform load. Now, it's not like a concentrated load at 900. We're going to use the triangle. So it increases steadily more and more as it goes from left to right. But we do know that at 6 foot, it results in a total force being applied of 900. So at that point, we go 600 minus 900, and we get minus 300. So I'm going to put another dot there. And then if we look from 6 feet to 12 feet, there is no force acting on it, so it's constant. It still maintains to be minus 300 all the way till it gets to B, and then it goes right up to 300. Okay, and this is the point where it gets 0, and that's what we want. All right, so at this point, now we got to decide how we're going to draw the lines for the shear diagram. And we got to take the cues from the shapes above, okay, that the loads are being applied there. So if we look at what's going on there, okay, we have a triangle. And what this triangle represents, okay, think of it this way. The value of that force acting on it is going to be a result of the slope of that line. So as it's going, as that force increases, okay, it's building up. So it's going to go from that 600, and it's going to go steadily down more and more and more, okay? So it's going to be going downhill. So it's going to be a parabola, okay? So it's going to be going from a slope of 0 at basically 600. It's going to go very, very steep as it approaches 6 feet. Okay, so that's where I'm going to draw the line as a parabola. Okay, so it's a parabola. It's going to go down, and it's going to cross somewhere. We don't know yet. It's some distance over x. It's going to cross with v equals 0. Okay? And then it's going to end up at minus 300 down there. And then we're going to draw a straight line across. All right? So we know how to get those lines in. All right, so now we got to find out where is x, okay? So we're going to break that out, and I'm going to show you a section view of this. So now we have a section view where we have the resultant force written there at 600 pounds. We have x, which we don't know yet. That's what we're going to try to find. And then you'll notice I have 50x. And where do we get 50x? Well, if we note, remember 300 pounds per foot, and it's over a distance of 6. So if you take the value of 300, okay, and you divide that by 6, okay, you're going to get 50. So x is the distance in feet, okay? And so we don't know what it is. So that's all we've done there. And then at the end, we have a shear force down, okay, which we're going to be looking for. And we have a moment, okay? So let's do a summation of forces in the y, okay? We get 600 minus, okay? So what is the minus? It's that non-uniform force. Well, we don't know what x is, but we know that the area of that triangle is going to be 1/2 50x, which is the height, times the base, which is x, okay? So we know what that is. We know that magnitude. And then we also know that we also have v down, so minus v, okay? And so and that's equal to 0. So now we're going to take that and we're going to solve for v. V is equal to 600 minus 25x squared, okay? And then what we're going to do is we're going to set it equal to 0 because we're trying to find where it crosses v, and when we cross that datum, that means v is equal to 0. So we set it equal to 0, and we get 600 minus 25x squared. Then we solve for x, and we get x is equal to 4.899 feet. So that is the distance over that the shear crosses over at 0. Okay? And so now we've got that down. And what we want to then do is then identify in here, okay, the positive, which is in that upper area there, then negative, that small little area there, and then that rectangle negative. So those are my things. Now what I'm going to draw is the moment, okay, the moment diagram. And what I'm going to do there is I'm going to draw a couple points, okay. So the first point we know is we're going to start at 0. And we're looking above there, and we're trying to find out. So what I'm also doing is I've drawn a dashed line down, okay? And that's where it crosses v equals 0, okay? It goes from positive to negative. What this tells me is that's where it peaks. That's where it's starting with a positive, okay? So it's increasing, and then it decreases. So the peak for this particular beam is going to be located 4.9 feet over, okay? So that's why I draw that dotted line down. So I know it peaks there. And what I want to find out is the value of that line there. And then also I want to find out the value of it where it transitions from a parabolic slope type thing, a curve, to a line. Because when it goes from 6 feet over, you'll notice that's a rectangle there, and therefore it's going to be pretty much a straight line. Okay. So what I need to do now is determine that. But what I also want to show you is another way of getting that 4.9. As you note that if we use the equation for a parabola, okay, y is equal to a times x minus h squared plus k, okay, and because this peaks, or its inflection point, is at 0, x of 0 and a y of 600, we know that h is 0, k is 600. So it further reduces that equation of the parabola to y is equal to ax squared plus 600. And we can solve for a because we know it also crosses a point on the parabola of 6, minus 300, and we get a is equal to 25. We put that in as y is equal to minus 25x squared plus 600. Okay, and we can just substitute in y is equal to 0, and we get x is equal to 4.89, just like we got before when we did the section. Okay, and you can see that those equations are the same, okay, that we got using the section method and just plot or calculating the equation for the parabola. All right, so now we're going to find what that moment is there. So I want to find out the moment at 4.90 feet. So I'm going to do the summation of moments, set it equal to 0, and I get m plus 1/2 50x times x. Okay, what that is, that's the force of that non-uniform load. And so I'm going to then multiply by the distance. Okay, in this case, the distance is 1/3 x. Okay, so whatever that is, it's 1/3 over is the moment arm that it's going to be. And then minus 600x, whatever x is. In this case, we have set it. We know what it is. X is equal to 4.9. And so we get moment is equal to 600x minus 25 divided by 3x to the third. Now, you'll note, and you look at that equation, that's kind of interesting, because if I had taken the equation of my parabola, which I determined earlier, and then multiplied by x, that's what I get. And again, what we're doing is we're calculating the area under that parabola to get our moment value. Okay, so then I put in 4.9, and I get my moment is equal to 1,959.6 pounds-foot. Okay, so that is the peak. And then I also want to find my value at x is equal to 6. I put it in the same equation, and I get m is equal to 1,800 foot-pounds. And so now I'm able to plot these two values. One is 1,960, and one is 1,800. All right, so what I'm now doing is I'm going to be drawing the curve from 0 to 1960. Okay, and I know that just looking above, it tells me that it is positive, but it is a high number, 600, so it's a steep curve to start with, and then the curve or the slope value of that line approaches 0 and actually reaches 0 at a distance of 4.9. So it starts out fairly steep and then transitions to very flat at the very top there, a distance of 4.9 over, and then it goes negative. That's where that negative on the shear diagram tells me, and then it starts, fairly flat and then goes a little steeper, and then when it reaches the 6-foot mark, you see it's a rectangle. Okay, so it is the same slope, so that means it's a line. So from 1,800, it goes straight down to 0. And there we get our moment diagram.